Here. So you're talking to me? Yes. You only called that one, the one in that one, they believe it.
I really start on the half hour, not a couple of minutes after that. Start right on the half hour.
Yeah, we start from, when the actual.
Good, okay, so I'll start now. My name is Dick Gross, and this is gonna be a graduate course on the interactions of L functions in number theory. And so today, I'm just gonna give you an idea of what I'm gonna cover, how I'm gonna cover it, that kind of question, and some of the features of the course and schedules and things like that. And then I'll really start the lecturing next Tuesday. So the course will be Tuesdays and Thursdays, that's easy. From 11:30 to theoretically 12:45, although I may sometimes go 5 minutes later or 5 minutes less, we'll see. And I'll just lecture during that time period. So one reason I chose this time is that on Thursdays, there's a number theory seminar following the course, and you probably, if you're interested in this course, will want to go to the number theory seminar. The talks may seem, when they're announced, kind of esoteric, but if you go to enough of these talks and you listen to enough of the buzzwords, you'll start to feel more comfortable about it. So today there's a talk, for example. And in fact, there are two talks. There's a pre-talk, which sort of is supposed to be aimed at grad students to give us some idea what it's about. And that goes from 1:15 to 1:45, I believe. And then there's an actual seminar at 2. And that takes place in this room, right, Lena? Everything? Yep. Okay, so you don't have to go anywhere. You can just sit here for half an hour and go to the pre-talk, and then sit here for another 15 minutes and go to the talk. And I strongly encourage you to go to the number theory seminar beyond the course. And the second thing I strongly encourage you to do is to register for the course. Now, what will that actually involve? I don't know the grading system at UCSD. I'm new to everything, but I've been told that it's very important that everybody register, because then the math department gets credit for having this many students in this many classes, and that's good for us. But also, I will, the only requirement for the course is that if you want to get a grade, if you're registered and you want an actual grade, for example, you might be an undergraduate, you really need a grade, then I'm going to assign, as we go along, various paper topics, and I'll be happy to read your paper at the end and give you a grade for it. And the paper would be about 10 to 15 page paper on some topic in mathematics that I've sort of glossed over and that you've covered in more detail by reading. So the only requirement is a paper. And there'll be no homework. I would say 10 to 15 pages at the end of it. And I'll suggest some topics, and if you have a topic that's one of your favorites and you want to do it, you can bring it to me and I can okay it, and it'll probably be fine. Okay, so that's the actual physical surround of the course. What am I going to cover? Well, I'm going to try to show you how L functions came into number theory through the work of 3 really great classical mathematicians. First the work of Euler, who was the person who introduced L functions to number theory in a series of papers running from 1737 to 1749. I'll summarize some of those results for you. And then, surprisingly, the great number theorist who followed Euler was Gauss, who worked at the beginning of the 19th century, but Gauss didn't do that much with L functions. The next real advance was made by Dirichlet in the 1830s, 1837, and I'll say today what Dirichlet introduced and what we'll study. And then the final A great paper on this was written by Riemann in 1858, sorry, just about the Civil War. And I'm going to introduce the ideas that Euler and Dirichlet and Riemann brought into the subject in their historical context. Namely, I'm going to show you how they prove things, or how they sketched proofs of things, because Euler really didn't have proofs in the sense that we would have. And it was surprising to each of these people, and certainly to Euler, who had no one else working on the subject, so he was just following his nose, and this is interesting, and that's interesting, and Dirichlet was also quite alone. And by Riemann, the subject was pretty firmly entrenched in the middle of number theory. And as I say, I'll just give you the lay of the land on this. After Riemann, there were a number of great mathematicians who worked on L functions in the 19th century. For example, Benedict generalized the results of Dirichlet on his class number formula, Weber, Kronecker. But we'll probably skip ahead after these three and then turn to the work of Hecke, Erich Hecke, in the 1920s, where he was the first to prove the functional equation of the generalizative function. And we'll probably do Hecke's work in the modern interpretation, which is called Tate's thesis. I'll sketch that for you too, which was written in 1950, which is a reworking of Hecke's ideas on L functions using Adels. And I'll introduce them to you too. And then after we do Tate's thesis, we'll go back into the 1920s and study the ideas of Abel Artin, who generalized the classical L functions that have been studied by Dirichlet and Benedict and Weber to a new type of L function called an Artin L function. And finally, if we have time, we'll do the L functions of elliptic curves. And that comes from the 60s. So these are all important topics in number theory. Elliptic curves, number fields, and L functions are a way of tying things together with them. So that's what I hope to do in this course. And I'm also not going to give detailed proofs of a lot of statements. Sometimes I'll go into more detail than others, because all of these things have been written up in a million different books. And if you wanted to read a book that sort of prepared you for the general assumptions of this course, and people have written me about that, I would suggest very strongly you get a copy of a book by Pierre Samuel, Algebraic Theory of Numbers. I think that's the title. It might be Algebraic Numbers. That does an introduction to the subject. What is a number field? What is the ring of integers? What are prime factorizations? What's the class group? What's the unit group? Those kind of questions. And I'm going to assume that people have that background. I mean, I'll review it very briefly, but this is not an introduction to number theory course. This would be the sort of background. Another very good piece of background, especially for the work of Dirichlet, I'm going to do is a book by Jean-Pierre Serre, A Course in Arithmetic. So if you've had this level of graduate course in number theory, then you're certainly going to be able to understand what I'm doing. And if you haven't, you may be able to acquire this as we go along, but it would require a little bit extra reading. And when we don't do a proof of something, I'll refer you to a book where there is a proof of that, so you can find nothing that I'm going to do is new or surprising or anything. It's just, the course is really intended more to give people an idea of the lay of the land in number theory, why L functions have played such an important role. Okay? So let me start with Euler and give you an idea of what we're going to prove, what Euler did about the zeta function. So the zeta function is a function of one variable, which is usually written like this. So it's an infinite sum, and this sum converges. Euler studied this in the region where s is bigger than 1 is a real number. you can show that the series converges in that region. It's a series of positive terms. It converges, but that it diverges as s tends to 1. So it gets larger and larger as s tends to 1. Euler knew that. It goes to infinity as s gets closer and closer to 1 from above. Because that s equal 1 is the harmonic series which diverges. And again, Euler had no one else that was studying this function and really didn't study it as a function of s at all. I mean, he just studied it in the neighborhood of 1, and he studied it for positive integers. Okay, so what was the first result he proved? Well, the result that made Euler famous in Europe, he proved in 1735 that the value of zeta at 2, which is by definition 1 plus a 4 plus a 9 plus a 16, etc., that infinite series converged pi squared over 6. And we'll take a look at his proof, which isn't a proof at all. It's a real hand-waving argument, and he knew it was a hand-waving argument, but he was convinced by it because before he actually proved this identity, he had computed both sides to 20 decimal places. So he knew before, this was already in 1731, he was able to evaluate zeta of 2, namely this sum, as 1.644934, and on to 20 decimal places. So the first thing we're going to do is we're going to learn how the hell Euler was able to make this computational load, because and how also he calculated pi to 20 decimal places. So we'll do a little bit of computing infinite series and tricky ways of computing infinite series, because this thing is obviously converging rather slowly. If you took the first 10 terms of this series, you'd be accurate only to within 1/100th of the answer, the second decimal point, right? Well, Euler, I'm going to show you how with 10 terms of this series going up to 1/100, we can get this level of accuracy. So that already was pretty cool. But then when he proved this identity, it went around Europe quickly, and he was a young man, and he became justifiably famous. And then he doubled down on that, and we'll see that the so-called proof that he gave for zeta of 2 works for all the even integers. He also proved that, for example, that zeta of 4 was pi to the 4th over 90, and that in general, the value at an even integer was the same power of pi times some rational number, and he made tables of these rational numbers up to about zeta of 20. So he actually knew how to compute them, and they get quite complicated. For example, when you get to zeta of 12, you already get a number which is pi to the 12th times 691 divided by 3 to the 6th, 5 cubed, 7 squared, 11 times 13. So Euler also knew exactly what primes were in the denominators of these numbers, but he realized that the numerators were quite mysterious. Like, this is the first even value where the numerator is not 1. Okay, so that was his first encounter. And well, then, second thing he did, so this we'll do both this estimation and this value. Second thing he did was, in a letter to Goldbach, he noted, this is also in 1737, this has to be one of Euler's greatest discoveries, and Euler made a lot of great discoveries. He noted that this infinite sum could be represented by an infinite product. The product over all the prime numbers of 1 minus e to the minus s inverse. So this is an infinite product. You have to prove it converges. He proved it converges again when s is a real number greater than 1. So this number, so this p to the minus s is less than 1. So this is a non-zero constant. And he proved that you could take the product over all of them if the individual terms converge to 1 fast enough, so this infinite product converged. That's called nowadays the Euler product for the Riemann zeta function. And this immediately gave him the first actually new proof of this great theorem in Euclid that there are an infinite number of primes. In Euclid had a method of constructive by contradiction of proving there are infinitely many primes, but this is another proof, because if there were only finitely many prime numbers, this would be a finite product, right? And consequently, it would converge at s equal 1. But this doesn't converge at s equal 1. So there have to be infinitely many primes. And in fact, Euler proved much more than there were infinitely many primes. He proved that the sum of 1 over p, or p less than x, diverges as x goes to infinity. So not only is the harmonic series divergent, that's the sum of 1 over n, and less than x, that diverges, but you can just replace it by the prime. So that's qualitatively more information than the existence of infinitely many primes, because there are infinitely many squares, but the series of 1 over the squares converges. So there are more primes than there are squares. Okay, so we'll do that. That'll be the first thing we do with Euler's work. Okay. Then again, to him, this was a curiosity. He didn't know that this was important or it wasn't important, but for us, this is going to be one of the most important things about zeta functions, is they can be written as products over primes. And then, and this I think is another one of his greatest papers, 1749, and he wrote a beautiful paper where he studied the zeta function at negative integers. So here, these are the values of zeta functions at positive even integers. But Euler realized he could find a formula for zeta function at 1 minus n, where n is an integer greater than or equal to 1. So zeta of 0, for example, was minus a half. And zeta of minus 1 was minus a 12. And zeta of minus 2 was 0. And on and on. He found formulas for this. And he found that they were always rational numbers. Now you might say, what does he mean by zeta of 1 minus n? Well, you know, Euler, because the series doesn't converge there. For example, at s equals 0, this is essentially saying, in nonsensical terms, that 1 plus 1 plus 1 plus 1 is equal to a half, minus a half. And this is saying that 1 plus 2 plus 3 plus 4 plus is minus a 12th. So that's not what he meant. He had some way of reinterpreting what this would have been, what this sum would be, and we'll see how he did it, and evaluating it, but he didn't have any notion that we do nowadays of complex variable theory or analytic continuation, but he was able to find this formula, and not only did he find a nice formula for it, but he found there was a relation between his formula for zeta of 2n and his formula for zeta of 1 minus 2n. I mean, they weren't equal because this was a power of pi times a rational number and this was a rational number, but they were related. And he guessed, and this is even more amazing, that there might be a formula between zeta of s and zeta of 1 minus s, whatever that means. And that's the so-called functional equation of the zeta function. Euler didn't have it, but he wrote down a relation that he thought would hold between this and this, if he could only define this properly, and checked that it was true for integers. Okay. So that's what we're going to do in Euler's work. We're going to show how he found formulas here, we're going to evaluate them for the first few negative integers, and we're going to see some relationship between these two things. And again, there was really no one Euler was writing to or publishing with that had any appreciation of this at all. I mean, for him, this was just curiosity. This wasn't curiosity. People were interested in the distribution of primes, and this certainly wasn't curiosity because it had been a big open problem before Euler treated it. But these relationships between the positive integers and negative integers, nobody really knew what to do with them. Okay. So that's the work we're going to cover in Euler. And then, as I say, the next person to really take up Euler's work, and it was again in the study of primes, was Dirichlet. And Dirichlet proved a great theorem, which had been conjectured and by Legendre and been used by people, where you said that fix a modulus n greater than 1 and a class A, which is relatively prime to n, then there are infinitely many primes P with B congruent to A on it. So let's call primes in an arithmetic progression. So as an example, there are infinitely many primes, but if you divide them into classes mod 4, there are primes which are 1 mod 4 and 3 mod 4, and it turns out both of those have infinitely many primes, and he gave a qualitative statement about how many primes there were in each one of these classes. And to do that, he introduced a generalization of the zeta function. Called Dirichlet L functions, L chi S. And these were associated to characters of a multiplicative group mod n, a group that had been studied by Gauss. So in that sense, Dirichlet carried around a copy of Gauss's work all the time. He was a complete devotee of Gauss. So if you had a homomorphism from the multiplicative group mod n to the complex numbers, he defined a Dirichlet L function as the sum of chi of n over n to the s, from n equal 1 to infinity. Now, this is a finite group, so the values of a character take values in roots of unity. These are roots of unity. In particular, they have absolute value 1. So this series is absolutely convergent for s bigger than 1, the same way that the zeta function is. And you only sum over the primes and the, sorry, bad notation, sorry. Let's do a character mod f. And you sum over the integers which are prime to f, because otherwise you can't evaluate chi. So this again converges for s bigger than 1. But Dirichlet noted that this actually had a larger area of convergence. And if chi is equal to 1, if it's the trivial character, if f is equal to 1, you just get the Riemann zeta function back. But if chi is not 1, then Dirichlet observed that this actually converges for s bigger than 0. So in the larger thing of convergence, there is no pole at s equal 1, like there is for the Riemann zeta function. And Dirichlet proved, to prove this theorem here, what he had to really prove was that the value of this at 1, which is well defined by this convergence, was non-zero. And we'll do that. And then, even better, he found formulas for the value at 1. He not only proved it was non-zero, but he found these beautiful explicit formulae, and he used that to study what he called Gauss's theory of binary quadratic forms, or what we would call quadratic fields, applied to study quadratic fields, which are fields of the form where you adjoin a square root of an irrationality to rational numbers, and he showed that to each such quadratic field you had a character of z mod dz star, where the values weren't in the complex numbers but were in plus or minus 1, so a character of order 2. And he showed that you had a notion of the zeta function of these fields like the Riemann zeta function, and it was the product of the Riemann zeta function and his Dirichlet L function. So we'll do that. Okay, so two associated quadratic character, and this relationship between the zeta function of the field and these Dirichlet L functions was Dirichlet's analytic restatement of Gauss's theorem on quadratic reciprocity. So we're going to see how quadratic reciprocity implies that, let's call this field K, that the zeta function of Ks, which we'll have to define, is actually the product of the Riemann zeta function and Dirichlet's L function. And so formulas for the value of this at s equal 1 gave a formula for the residue of this at s equal 1. This turns out to have a simple pole at s equal 1, and we'll do that formula. Okay, and then finally Riemann, who had, so Dirichlet, Euler really only considered these as functions of a real variable, and really only considered them for s greater than or equal to 1. I mean, Dirichlet didn't really study it in this entire plane, but Riemann showed that, first of all, that, and we'll do this too, that zeta s has a meromorphic continuation to the entire complex plane minus 1. It has a simple pole at s equal 1, and that these L chi s, Dirichlet's functions, where chi was not the trivial character, has a holomorphic extension to the entire complex plane. No poles at all. And with that extension, he proved there's a functional equation relating L chi of s to L of chi bar, the conjugate character at 1 minus s. And that generalized Dirichlet's functional equation. And finally, Riemann was very interested in this function. He identified its poles, what were its zeros, and he showed, he conjectured the only zeros of L chi s for, say, real part of s greater than 0 have real part of s equal to half. And that conjecture is still open. That's the Riemann hypothesis. And we're going to see what Riemann did relating the zeros of this function to the distribution of primes. This old question that Euler had started, that there are infinitely many primes, that the sum of 1 over p diverges. Riemann had much finer estimates for the distribution of primes if one only could identify where the zeros of these functions were. And people made a little progress. For example, by 1890, after Riemann's death, mathematicians were able to prove that, for example, L chi s is not equal to 0 for the real part of s equal to 1. I mean, that's a generalization of this. I mean, this is just at the point s equal 1, but if you consider this a function of complex variable, at least on the line where the real part of s is equal to 1, it's non-zero, and that's more or less equivalent to what we call a prime number field. So I'll do a little of that. Okay, and then, based on the work of Riemann and Dirichlet, Benedict generalized the notion of the zeta function of a quadratic field to the zeta function of an arbitrary number field, where instead of summing over integers, Benedict's zeta function summed over the ideals in the ring of integers, and 1 over the index of the ideal in the s power. Ideals which are not zeros. And such ideals have finite index. In the integers, the ideals are all principal. They're given by multiples of n, and so this is just n to the s. But Benedict realized this was an important invariant, and we'll study the zeta functions of number fields. And it was Hecke who was able to finally generalize Riemann's argument and prove that this function had a functional equation when s was replaced by 1 minus s. And that's where I'll bring in the notions of Adels and Edels and Case thesis. Okay, that's basically what I plan to do. As I say, I'll try to give at least hand-waving arguments as I go through. I'll try to give references, but at the end you should get some feel as to why L functions are so important in number theory, what the open questions are, because a lot of interesting questions in number theory now concern L functions. I mean, obviously, the Riemann hypothesis remains as maybe one of the central questions in mathematics. And I think that this looks, it's funny, all these things look like they're analytic statements. I mean, when does a function vanish? So, you have the complex plane, and you have the point s equal 1, and you have the functional equation that flips around the line s equal a half, real part of s equal a half, and the zeros are supposed to be somehow concentrated on this line. And so far, all the zeros that have been found, and there have been millions of zeros found, are pure on that line. And it looks like, okay, fine, that's an analytic question, and maybe we can answer it by doing some little contour integral around here and discovering that there's 1 0 inside of that contour, and then making it a smaller contour, and then making it a smaller contour, that kind of thing. But if you think about it, analytically, you can never locate the zero of a complex analytic function. You can approximate the zero. You can say it's you have a 0 and s equal a half. Well, it's really, it's like our students' homework. You have a 0 at this point, but then you don't know what happens after that, right? And if this was a 1, that would be bad. And so all the methods of complex analysis can't really resolve these questions. They're somehow algebraic questions, and we're going to see that. And I think to really resolve the Riemann hypothesis or questions of that nature, you have to know what these zeros mean, and that's what we don't know. Nobody knows really what they mean at this stage. And so you can prove things are non-zero analytically, and we're going to see how you prove things are non-zero. That's easy. You just have to show that one of these decimals is non-zero, and you can stop it. And you can't prove anything is zero analytically, and you certainly can't prove that you have a multiple zero. So another conjecture that people like to believe is that the zeros of the Riemann zeta function are simple, and you don't get any double or triple or quadruple zeros. But how would you ever, if you think about it, distinguish a triple zero from 3 zeros that were incredibly close to each other? Because every time you did a contour integral and counted the number of zeros inside, you'd come up with 3. But how do you know they're at the same place? So a lot of these questions about zeta functions that appear to be questions in analysis are, in my opinion, probably questions, deeper questions in number theory, and we'll try to address that and get, that's the fun of the subject really, is the interplay between the analytic side, where you have infinite series and infinite products, and analytic continuation and things of that nature, and the algebraic side, where you get factorizations like this. So that's the summary of what we'll cover, and on Tuesday I'll start off with Euler's work and how he proved that there are infinitely many primes and how he proved that series diverged and so on. Questions about the course in general? No? Okay, so and I should just say sort of what kind of things might be good for papers, okay? So, when I said that Euler's, I'm going to give you Euler's method for calculating zeta of 1 minus n, but you're going to see that that's a completely illegal thing. And what I'm doing, like the 19th century, the mathematicians like Abel just went crazy. What is he doing? So we now know how to do this using complex analysis, because once you have a meromorphic continuation, you can try to study it at negative integers, and that's what people did. 0, -1, -2, -3. Those seem to be very interesting points. So that would be a typical paper. The values of zetas at negative integers, and maybe their p-adic properties. They give rise to things called p-adic alpha. And then we're going to see that Dirichlet used this factorization and his formula for this function at 1 to study the class groups of imaginary quadratic fields. This is the best information we have on class numbers, class groups, etc. So you might do the class number formula. That's the general formula for the residue of this at s equal 1. So that would be another type of paper you could do. Or when we do Riemann and we do the factorization of this according to the zeros of the zeta function, so you get 2 product expansions for zeta function. You get the Euler product over the primes, and then you get the factorization of this as an entire analytic function of degree 1, so it can be written as a product over its zeros. So you can go from those 2 factorizations to all kinds of beautiful formulas relating the primes and prime powers to the zeros of the zeta function. Those are called explicit formulas. So that would be another good paper. Or when we do the functional equation of this function and Hecke's L functions via the del's and del's, you might do a report on Tate's thesis. I mean, I'll just wave my hands at it, but you have to do some Fourier analysis. It's a really beautiful thing. Or when we get 2 L functions of elliptic curves, you might write a paper on the conjecture of Birch and So that's the level of papers I have in mind, people want to take the course. Okay, and I promise I'll even read them. Okay, so I'll see you all next week on Tuesday, and make sure to take advantage of the number 37 activity because it looks very interesting, and it's given by one of our comrades at UCSD. Right? Alina, anything to add?
Oh, register for the seminar.
Pardon?
You guys should register for the seminar, not just the course.
Ah.
Because then we get money to bring speakers from.
That's what I should have said. Not just, the course is irrelevant, but register for the seminar. Okay? Okay, so you're all good.